Hello. Hi. Just to let you know that we are having some technical difficulties because why not? Every day brings a new challenge to the world. So the way I was doing my old videos is not available right now until they fix my laptop. So right now I'm back in room 22 using the whiteboard and using my cell phone camera. So we'll see how this lesson goes. This is the best I can do right now for explanation. So we are starting a new unit today. It's technically unit 3B. We just finished our derivative unit. So now that you guys know your derivative rules, now we apply them. Now the good news is there's actually only 2 lessons to this unit. The first one is the rate of change motion problems is what we will do today. And then the other one is something called related rate problems. So just 2 topics that follow. So it'll be a nice, short, easy unit, and we'll have some kind of assessment at the end of these 2 units. And again, we don't know exactly what's happening with the university, but traditionally, this is where the midterm would happen. Once you do related rates, that's the midway point of this course, and the midterm covers everything from limits, derivatives, up to related rate problems. So technically, once we finish this unit, we are halfway through the course. Okay, so 2 topics. Today we will look at rate of change motion problems, also called rectilinear motion. I do believe all 3 of you are in physics, so this will be a nice good comparison to what you're doing in physics, so you know a lot of the language and terms that we'll be using today. So rectilinear motion, it's just motion in one dimension. So we're looking at an object or particle that's moving in a straight line. So we're just going to do one example together. They're kind of long and tedious, but I actually think it's fun. We're taking all of the rules that we learned, like last unit we just said here are the rules, use them, but now we're actually applying them to a real life application and seeing and where and how they get used. So there's 3 things that we need to know. So ST, that would be the original question that's given. So the original equation, that gives you the position of an object at time t. So the initial equation, S of t, gives us our position. Then the first derivative, S prime of t, the first derivative gives you velocity. And then the second derivative gives you its acceleration. I'm sure you've heard these terms many, many times, especially in physics. So the original function gives you its position, the first derivative is velocity, and the second derivative is acceleration. So I think it's fun. We're putting all these things together to get the position, velocity, and acceleration of a particle. So before we get to our example, I've just kind of broken it down into a few steps. So how do you solve a rectilinear motion problem? Like I said, they're not hard. They get a bit lengthy, but every step is connecting to each other. So you'll be given ST, that was the original function. Then you have to get the first derivative. These will be easy. This isn't even no chain rule, no trig functions, just straight old easy first derivatives. We still did that back when we were together in a class here. So the first derivative would be really easy. The first derivative will give you the expression for velocity. Then you're going to take your first derivative and set it equal to 0. Now, you're in physics. I know you know what that represents. When you set the velocity to 0, what does that represent? That tells you that's where the particle stops, when the velocity is 0. So that'll be important information as to get. Then, once you know where the particle stops, you are going to substitute them back into ST. Not the derivative, the original equation. When you substitute those values back into the original equation, that gives you the position where the particle stops. So the first derivative tells you when it stops, then you substitute back to get where it stops. Then the next step, sign diagram. We did do that back in grade 11 pre-cal. We did have a worksheet on sign diagrams. I'm assuming all 3 of you did your homework and understood that. In case you forgot, I'll just email you a copy of the exact same worksheet we did back in grade 11, and I'll email you the notes again in case you forgot how to do a sign diagram. Sign diagrams will come up quite a bit in calculus, especially when we go into curve sketching next unit. So once you set up your sign diagram, and the sign diagram, it's based off of the velocity. So the main thing is just keeping track of your work, make sure you know what each step is representing along the way. So when you take your first derivative, which is velocity, you use that to get your sign diagram. Any regions on your sign diagram that are positive, that represents where the particle moves to the right. And then any region on your sign diagram that's negative, that shows you where the particle is moving left. And then the final step is draw the diagram. In the notes that I gave to you, I think I had a section about acceleration. I'm just going to leave that out. You're in physics, so maybe you could want to do that extension a little bit just to verify it. But if you do these 5 steps, this should get you to the final answer every time. Okay, So we're just going to do one example together. Like I said, they're lengthy, but they're not hard at all. The derivative work is really easy, and the fact that all of you are in physics means you have a good concept of acceleration velocity. So I know that this topic will be really easy for all of you. Okay, so the first thing we do is, I didn't write out the actual question, it's in your notes. We have a point, it's moving along a horizontal surface, and the formula has been given to you. So this is the formula that represents the motion of our particle. So before we begin, I'll just rewrite it. The original equation is going to represent for us the displacement. Displacement, position, that tells us, that's the equation we'll use to figure out where the particle is. Then let's get the first derivative. This should be really easy for us compared to that last hand-in that we just did with all those fun derivative rules. Really easy. This should give us 6t squared minus 42t plus 60. And that's it. Remember how nice and easy those derivatives were about a month ago? That's our first derivative. Now what does that represent? That represents the velocity of the particle. And when we use functional notation, instead of s of t, we might use v of t to show that it's velocity. Or you can use s prime t, it doesn't matter. Then let's take the derivative of the derivative. We did have a lesson on higher order derivatives. So the second derivative would be 12t minus 42. I told you the derivative work is really easy in this lesson. What does that represent? That represents its acceleration. And you can call it s double prime t or a of t for acceleration. So you've got your displacement, your position function, your velocity function, your acceleration function. Okay, now what do we do with them? How do we use them? How do we get a diagram out of these three functions? Well, the first thing is to set your velocity function to 0. Like I said, you're all physics students, so you are very good at the notions of velocity and acceleration. So when we set it equal to 0, that shows us where or when the particle is not moving. Now we go back to grade 11 pre-cal and we factor this. We can factor out a 6. There's a common factor. We factor that out, and I know that you all know how to factor. Remember how easy grade 11 math looks now? Quadratic function seems hard at the time, but now, oh, this is easy math for us. And then we solve. So we have two solutions, t equals 5 and t equals 2. So those are the two times when the particle is going to stop. Okay, now how do we use that information? Now we use that information, we take those values, now we go back to s of t. That one gives us its position or displacement. So the t equals 5 and 2 tells us when the particle stops. Now we need to figure out where the particle stops. So we replace our two values in. So first you replace the t's with 2. You could do some fun mental math at home since I'm sure you're bored. If you do it correctly, you get s of 2 is 55. Then the next, so this is where its position is when the time is 2. Then we do the exact same thing, but we need to replace all of our t's with 5. That was the other time when the particle stopped. Again, you can do all the fun mental math on your own, but if it's done correctly and if the pen works, that is a 28. So when time is 2, its position is 55. When time is 5, its position, that is a 28. Okay, what does that mean? Well, nothing quite yet. We're just doing the pieces at a time. We'll eventually put it all together in one diagram. So now we know where it stops, and now we know when it stops. Now we're going to put it together and do our sign diagram for velocity. So I'm going back to the factored form. This is our v of t, remember, our v function, or that was our first derivative function. Grade 11 pre-cal, we learned that you get your key points. The key points are anything that makes the expression equal to 0. So our key points are 2 and 5. Then we take a large key point, any key point larger than our largest key point. So any number greater than 5, we like to use a million because that makes it more fun. When we run a million through, we don't really care what the number is, but 6 times a million minus 5 times a million minus 2 gives us a positive number. It's a sign diagram. We don't need the values, we just need to know the sign in that region. And then we move right to left. Oh, the first key point we hit is 5. What's the exponent? Exponent is 1. When it's odd, you change the sign from the previous region. You keep going, the next key point you hit is 2. What's the exponent? The exponent here is odd, change it again. And that is our sign diagram. Hopefully it's coming back to you. We did spend some time in grade 11 pre-cal learning this. So what does that mean? From time minus infinity to 2, the particle here will be moving right. When time is between 2 and 5, the particle is going to be moving left. And from 5 on, the particle is going to be moving right. Okay, I think we're done all the math part. Now we're ready to put this together in one diagram. I really do find these fun. I find it really fun to solve and then put the pieces together. So we know that there's 2 spots. It stops at 5 and at 2. Now you might think, oh my gosh, Miss Cooley made a mistake. She has been without the students in class. She doesn't know that 2 is smaller than 5. I do. I put them in here because this tells you when it stopped, but you need to put it in order of where it stops. Remember when our time was 5, it had a displacement of 28, but when the time is 2, it had a displacement of 55. So 28 is smaller than 55. So you put them, and that's why we needed our position. This tells you when, this tells you where it stops. And our sign diagram was on the previous side. We said up until 2, the particle is moving right. Then at time is 2, it stops, and then it starts to move left. And then at time equals 5, it stops again, and then according to your sign diagram, it moves right. And there you go. That's our diagram that shows the motion of that particle.